Hi all. The next portion in module 3 is strongly connected components. From the name itself, it gives you an idea that these are methods to connect strongly related components inside a graph. A directed graph is strongly connected if there is a path between all pair of vertices. A strongly connected component, short formally known as SCC, of a directed graph is a maximal strongly connected subgraph. Now, as in this example, it is shown that 1 to 0, 0 to 2, 2 to 1. It's a cycle basically. Those are strongly connected. Another connected one is 3 and 4. Those can be separated. Now coming to the topic, a strongly connected component of a directed graph is represented by G is equal to V comma E. As you all know, V is a set of vertices, E is a set of edges, is a maximal set of vertices C subset of V such that for each UV and edge in C, U and V are reachable from each other. U to V or V to U. They are mutually reachable from each other. Let G of T or G of transpose is represented by V comma E transpose. The number of vertices or the format of the vertices never change in any graph for a particular graph. So it is always a V as initially. Only the edges can be changed. Either it is from U to V or from V to U. So G of T is the transpose of G where E of T shows U comma V where U comma V belongs to E. That is, E of E transpose consists of edges of G with their direction reversed. Constructing G transpose from G, it takes O of V plus E time. That's a time complexity. Note, there is a note for this. G and G transpose has the same strongly connected component graph. U and V are reachable from each other in G if and only if they are reachable from each other in G of T. Only then you get a strongly connected component graph. Now the algorithm goes in this way. Run a DFS, that is a depth first search, using the graph to compute finishing times for all U and V. You get the finishing time U dot F, if you might remembering what we had discussed in DFS. Now using that finishing times, compute G of T or G transpose. Call DFS G transpose, processing vertices in main loop in the decreasing order of F of U computed in step 1. The finishing time that is computed in step 1. That is how you get G of T. Now output vertices of each depth first tree in a depth first forest of step 3 as separate strongly connected components. That gives you the answer. Now what is basically this algorithm all about? We can explain or we can try to understand using an example. Now in this example there are some nodes A to H and these nodes are interconnected to each other. Now you have to do or you have to perform the algorithm or the DFSs on all these, and you have to design the SCC, strongly connected component, which all are strongly connected components in this. The first step in the algorithm was run DFS to compute finishing time for all U and V. In this graph, C is taken as the source node, so the finishing time starts there. Try to recollect that DFS. Have you got it? The same procedure is carried out to find out the finishing time. This is how it does after one set of DFS. C to G, G to F. F doesn't have outgoing, so it comes back to G, backtracks to G. then it goes to H, nothing outgoing is there, it loops inside H itself, so completes it, comes to G, then it goes back to C and then to D. This gets completed. It doesn't go to the other end as A, B and E. So because there are white nodes or nodes with white color, you have to start the DFS again. As we had already discussed, the second part, you start from B, and this goes on for B to E, E to A to B. Again, this is a triangle, so it goes on. So vertices sorted according to the finishing times are finishing time. B has a finishing time of 16, E has a finishing time of 15, A has a finishing time of 14, C has a finishing time of 10, D 9, G 7, H 6, F 4. Now the next step in SCC is to compute transpose of G. Call DFS transpose of G, processing vertices in the main loop in the decreasing order f of u order. The u have already got the order, so in that order the traversal should start from, or the segregating of SCC should start from B. When it starts from B, B is taken. B is having an outgoing to A, as the green arrow shows. A has to go to E and E again comes to B. So this is one component. There is no outgoing edges going on. So the first three values of the order, that is BEA, is over. You don't have to bother about that. That becomes one strongly connected component, which is known as R1. Next is in the list or in the decreasing FU order, next node comes C. So you can start from C. C has an outgoing edge to D, which is shown by the green value. D again comes back to C. There is no other outgoing edge going out from D. So that becomes another strongly connected component. So C and D in the list is over. Then you start with G. Now G has an outgoing edge going to F, shown by the green arrow. It comes back to G again. This is a loop going on between F and G. So that becomes the third component. And the last one is H. You cannot throw it out, so that becomes the last one. So this is how the component looks like. R1 is equal to ABE, R2 is CD, R3 is FG, and R4 is H. This is represented using R1 is represented using CB, R2 is represented using CC, R3 is represented using CG, and R4 is represented using CH. These are the four different components for this particular graph, and this can be represented once again as a single node which has a combination of nodes CB, which is a set of ABE, CG a set of FG, CC an edge of CD, and CH an edge H itself. So how are these connected to each other? From the original graph you can see that CB is connected to CG as well as to CC. CC has a connection as in the node from C to G. So C to G is connected. That is how the names are put, abbreviations are put as who connects who. So CB and CG, that means there is a connection between G and B in the original one. and this goes on. So this is how a strongly connected component graph from a graph is calculated. You have to just go through the algorithm and the example. Thank you.